We have seen that chemical reactions can enter a state that we have described as a chemical equilibrium. In this video, we want to discuss exactly how we quantify that state, how we recognize it by its concentrations of the reactants and products. So our learning goals in this case are going to be to identify the equilibrium state from the concentrations of all the reaction species. Now I just want to remind you where we left off. We were talking about this reaction of NO with Cl2 to make NoCl2. And at the beginning, the two reactants decayed in a sort of a slope, whereas the product molecules were growing in. But they reached a point where they all plateaued out, and they reached a stage where we can describe all of their curves as being flat, and that's a state that we can describe as equilibrium. And we even define chemical equilibrium as the place where all the reaction species are constant in their concentrations. I want to define a quantity called the reaction quotient that sort of takes this into account. Now, if we have a dynamic equilibrium, it means that there is exchange going on with those smaller mobile units, the reactants and products, that is going back and forth between the two states. In some sense, we can describe this as a forward reaction and a reverse reaction, and the forward reaction is equal to the rate of the reverse reaction when this is happening. So if I were to develop some expressions for the forward rate, and I'm doing this without any sort of proof, but I want to motivate this a little bit with some intuition. And that is, when we have two molecules that have to collide in order to react, in some sense, the frequency with which they're going to collide is going to be proportional to their concentration in the solution. So if both of them are very concentrated, then there will be a lot of collisions and the rate will go fast. If one of them is not present very much, but one of them is, the forward rate won't go very fast because we're missing large parts of one of the reactants. If both of them are low, then the rate probably won't go very fast at all. So in some sense, when we have two molecules that need to collide in order to make a reaction, we can often write the forward rate as being proportional to the product of their concentrations. What about the reverse rate? Well, the reverse rate is NoCl2 falling apart. And in some sense, that's always going to be proportional to the amount of stuff that we have in there. If there aren't many NoCl2 molecules, then there aren't going to be many of them falling apart. If there are a lot of them, then more of them will be falling apart. So the reverse rate, again, is going to be proportional to the amount that we have in there. Now, I want to use these two to somehow equate the forward rate and the reverse rate, but I don't know exactly how they're equated with one another. So what I'm going to do instead is look at the ratio of these different pieces and see if I can set that ratio equal to a number that I can track as the reaction goes. Well, that number is the reaction quotient. So here we're defining a reaction quotient as the concentration of the NoCl2 divided by the concentration of NO times the concentration of Cl2. I want to note that the subscript C that's used here stands for concentration, because sometimes we may write the reaction quotient in terms of partial pressures, and then we would use a little p. I'm using a C in this case because we're going to be measuring things in concentration. Now, an interesting thing to do is to run some of this reaction and look at how this reaction quotient changes as a function of time. So what I want to do is set up several different reactions and see if there's anything I can learn from looking at the time dependence of this reaction quotient. So that's what's shown in this particular graph. Now I'll point out that the three curves, there's a green curve, a red curve, and a blue curve, they all represent different reactions that are run separately. They start with different initial concentrations and then they run. What's being plotted on the vertical axis, though, is that reaction quotient. It's that ratio of different reactant concentrations that's going on there. Now, you can see that there is a difference in the way they behave, but the striking thing about this graph is that all of these different trials level off and they converge to the same value on the right-hand side. Now, this is basically a sign that the forward rate there is equal to the reverse rate, and that happens at a particular value of this reaction quotient. And in fact, that value is something that, that constant value is something that we'll make note of because it's unique to that given reaction. It is not unique to the initial concentrations. Any set of initial concentrations will end up putting the reaction quotient at that same point. So as a result, the constant value that the reaction quotient has there is something that we call the equilibrium constant. It is a constant that characterizes the state of equilibrium. Now let's generalize this. I've done it for a very specific reaction, but if we were to have a general reaction of this sort, now I understand that this is pretty abstract, but if you'll imagine that A and B are some kind of molecules and they react with one another to make C and D, and when I make a balanced chemical equation out of it, I need those little a, little b, little c, and little d to balance the equation. Then in this case, I would have to define the reaction quotient like this. It's going to be the product of the two product concentrations, but they're each raised to the power of their coefficient in the balanced chemical equation. Okay, this is very important. You're going to need to use this formula, so I want you to see where it's coming from. They're divided by the product of the reactant concentrations, A and B, each of them raised to the power of their coefficient in the balanced chemical equation. Now, if we form this thing in this general sort of reaction, it will then turn out to be equal to a particular constant whenever that reaction reaches an equilibrium. So we're going to be using this quite a lot in solving some problems in this module, and I want to paint for you the typical scenario that you're going to be following for finding the equilibrium state. First, we're going to be most likely starting with some kind of initial conditions, initial concentrations. And we're going to allow those concentrations to shift, but they have to shift consistent with the balanced equation. In other words, we always need to have a balanced equation in order to fully specify the equilibrium state. The final concentrations then must satisfy the equilibrium expression, and that's the expression that's written up above in red, where the equilibrium constant, which is a constant number, is equal to that function of the various concentrations of the species that are in the reaction. So every time we get to an equilibrium state, that equation is satisfied. So that equation is what we're going to be using to solve for an equilibrium condition in a reaction.